Hello everyone. Today we are going to discuss on canonical forms of second order linear partial differential equation. This is the last chapter or last topic from partial differential equation part of the syllabus. Okay, so any second order partial differential equation which is linear obviously can be written in this form. This is all our second order term. These are all first order terms. Okay, so A, B, C, D, E, F, they are all coefficients. Basically they can be some functions, but here we will take this A, B, C, D, E, F, all are constant or real numbers. Okay, so we have more simplified situations. We have second order linear PDE where the coefficients are only real numbers, that means constant coefficient. Okay, so we have this type of PDE and we have to find its canonical form. So what do you mean by canonical form? Canonical form is like a standard form. This type of thing you have encountered previously, I think in class 11 or 12 in geometry, where you have second or second degree term, second order general equations in xy, and you have to reduce, or you have done that thing, that is you given equation, you have to tell whether it represents a parabola or hyperbola or ellipse or maybe some pair of straight lines. I think this part you have done in class 11 or 12. So any for example, any parabola, equation of any parabola is like y square equals to 4ax. This is the simplest form, but this is very typical parabola where everything is very standardized, but more general type of parabola which we can always write like y minus beta whole square equals to 4ax minus alpha, or sometimes x equals to ay square plus by plus c. This type of equations always represents parabola, but if you move the coordinate axis in such a way that you can reduce the equation of parabola always in terms y square equals to 4ax, you have to give some transformation, translation means translation, and some rotations, and you will ultimately you will get y square equals to 4ax. The same thing happens here. We have this type of equation. Okay, so we will reduce this equation in three types. Okay, similarly here types are hyperbolic, parabolic, and elliptic. These three standard forms are there, and they have very simple canonical form. You see there are 1, 2, 3, 4, 5, 6 terms are there, but you can reduce it. And how to reduce this thing? The simplest technique is to change the independent variable. You have to take some functions of this independent variable. So you take, suppose you take alpha and beta, be two functions of xy, and transfer it here, and you can reduce some of the terms depending on the constants. Okay, so the first order terms are this thing, second order terms are this thing. So canonical form is simplest form or the standard form. And how to get it? You get it by changing independent variables. So let me tell you that if we take transformations, alpha equals to a function of xy and beta is also a function of xy, we can transform this equation into other form. This form we can say in this way. This form, this new equations will be a1 del 2u del alpha 2, b1 del 2u del alpha del beta. In this way, you see all the independent variables change to alpha and beta, and this coefficient should also change, and the new coefficients a1 b1 c1 d1 e1 f1. And if you want to know what is the relation between these new constants and the old constants a b c d e f, this relation you have to memorize this for doing problems. This new relation is like this. First this thing will seem a little bit awkward, but this thing not that awkward if you carefully observe this thing. This f1 is same as f, e1 is nothing but the whole equation in terms of alpha beta. See these terms carefully. Similarly, d1 is the whole equation with respect to alpha. Obviously this f term is not there, just del alpha del y, del alpha del x, del 2 alpha del y2, this way. And this thing is partial derivatives with respect to x and y of beta. What is alpha beta? You know, alpha beta functions of this thing. So e1 f1 e1 d1 are clear. c1 is, see, it is the second order term, like c1 and b1 are more or less similar. They are only differed by alpha and beta, and b1 is rather different from others. You think this one we have to memorize for the transformations. Okay. So we have equations like this, and we take this type of transformation, and this new equation looks like this. Okay, so now one thing you should know, that when we say a differential equation is elliptic, parabolic or hyperbolic, this is the condition for that. So you have given the equation, you just identify these terms, these coefficients a b c d e f. You check this sign of this thing, b square minus 4ac. If this is greater than 0, the equation is hyperbolic. Equals to 0, the equation is parabolic, and less than 0, the equation is elliptic. So depending upon the type, you can classify. At once you see that you can classify the differential equation in 3 types, and correspondingly these all things become simplified. For example, if you take this hyperbolic case, it's very easy. You see, this is our old equation. Okay, so hyperbolic case is b square minus 4ac is greater than 0. You have given this equation, you check, firstly you identify a b c d e f, and then you calculate b square minus 4ac. If it is greater than 0, then this thing is hyperbolic, this equation is hyperbolic, and you at once know that this equation can be reduced to this thing. You see, 1 2 3 4 5 6 terms were there in the main equation, but after some transformation you can reduce to only 4 terms in this way. This is the standard form. Okay, so now if I ask, or someone asks, that what is that particular transformation by which you can change this equation to this equation, this answer is very particular in this case. You don't have to search, or we have to take these equations and do some simplifications. You don't have to. You just remember that whenever a is non-zero, that means this given a is non-zero, the transformation goes like this: alpha equals to lambda 1 x plus y, beta is equals to lambda 2 x plus y, where lambda and 1 and lambda 2 are the roots of this equation a lambda square plus b lambda plus c equals to 0. Where are what is ABC? ABC comes from that. They are all real number. This is second degree equation in lambda. You will have 2 real roots, basically because of this relation, and the real roots are this thing, lambda 1 and lambda 2. Whenever a equals to 0, b and c are non-zero, So in this case, this transformation is alpha equals to x, beta equals to x minus b by c by y. Still the equation is hyperbolic, but the transformation is slightly different. And whenever a is 0, b non-zero and c is 0, the transformation is a is x, b is y. So you have to memorize this transformation accordingly. So if you take this transformation, you can at once reduce this equation to these equations, and this d, e, f, how to find that? It's very simple. Basically there, this is d, d1 is d, d1 is e, and if we can find this equation, you can since you know the transformation, you can easily calculate d alpha del alpha del x or del 2 alpha del x2, and all these things you can easily calculate from these transformations, because you already know this transformation. We can already find these things, find the terms and put there, and you will at once get d, e, f. So you have given this equation, you can now at once write this equation. This is the standard form. So if you take an example, these things will be little bit more clear. Okay, so for that, suppose we have given these equations. This equation is there. So firstly we identify a, b, c, d, e, f, and it's very simple. This a, b, c, d, e, f. In these terms may be haphazard, but you must know that what a represents, what b represents, what c represents. This thing you should know, because a is the coefficient of del 2 del x2, b is the coefficient of del tu del x del y, and like this thing. So if you calculate b square minus 4ac, you will get 36. This is greater than 0. This is the equation is hyperbolic. Since it is hyperbolic and a is non-zero, b is non-zero, c is also non-zero, so if we take this equation in lambda square plus lambda plus c and solve this, we get lambda 1 equals to 1 and lambda 2 equals to minus 5. So the transformation becomes alpha equals to x plus y, and this beta equals to minus x plus y. Okay, this thing actually comes from the first result. If you remember, whenever alpha non-zero, the transformation is alpha equals to lambda 1x plus, and beta is lambda 2x plus y. Okay, so this comes from there. So now if you calculate what will be the value of a1, b1, c1, d1, e1 now, so if you calculate these things, you will get these things, because a1, this is nothing. If you remember this result or these formulas, you can at once calculate del alpha del x, del alpha del y, and all these things, all these derivative terms, and you can put it here, that here, and you can, if you simplify this thing, you will get this thing. So obviously the reduced equation will be like this. Okay, because see, this a1 is 0, c1 is 0, that means there will be no del 2 u del alpha 2, and c1 is 0, that means there will be no del 2 u del beta 2. So only the terms with coefficients b1, d1, e1 and f1 will survive, and that means b1, d1, e1 and f1, these terms will survive. So this is the required equation. Okay, this is the standard reduced form of any hyperbolic equation. Now the same things we are given with the same equation, and now in this case b square minus 4ac is 0, so the equation is parabolic. Now three cases can occur. a1 is non-zero, c1 is non-zero. In this case, transformation equals to alpha equals to lambda x plus y, and beta is y. So what is lambda? Lambda is the root of the equation a lambda square plus b lambda plus c equals to 0, and this is a quadratic equation in lambda, but since b square minus 4ac is 0, so the roots are equal, so you can always have lambda 1 equals to lambda 2, so one root of lambda 2 will be there. This thing we will use here. The transformation is like this. Now whenever alpha is A is non-zero and C is 0, the transformation is alpha equals to y, beta equals to x, no need of lambda. And in the other case, just yx and this xy is reversed. There is also no need of calculation of alpha, lambda. Okay, so the canonical form will be this thing, because if you calculate the reduced terms, reduced coefficients, you will get this. For that, you take an example of this equation, and which is obviously parabolic because b square minus 4ac is 0. We identify ABC is like that. Solve lambda equals to 3, and the transformation is like this. We calculate a1, b1, c1, d1, e1, f1 from that formula, and it will get these things and put, and you will see since a1, b1, these two terms are 0, so other terms will be there. Okay, so the reduced equation you see is of the form this, and this thing can be written in this way. This is the actually standard canonical form of any parabolic equation. Okay, this thing is basic, and the rest is elliptic equation. This thing is little easy, because here you have a given equation, b square minus 4ac is less than 0. So transformation is alpha equals to ax plus y and beta equals to bx. What is a and what is b? A plus ib are the complex conjugate roots of the equation a lambda square plus b lambda plus c equals to 0. This equation has complex conjugate root because of this relation you know from the coordinated equation. So the root is one is alpha a plus ib and another is a minus ib. This real part you put it here and the complex part you put it here, and the transformation is like this, and this canonical form is this thing. There is no cross term, that means del 2 del alpha del beta. This terms is there, only 5 terms are there. So we take an example. Similarly, we take an example of this equation. Okay, this equation, and you see that b square minus 46 minus 16, you can check this is less than 0, so it is elliptic equation. So you consider the quadratic equation, it become lambda square plus 2 lambda plus 5 equals to 0. So the roots become minus 1 plus minus 2y, so we have a equals to minus 1 and b equals to 2. So the transformation, this thing becomes this. Okay, it's very simple. And now if we calculate this changed coefficients a1, b1, c1, d1, e1, f1, it will become this thing. Okay, and obviously this is the reduced equation. You see one thing, one d1 is 0, so there will be no b term. Ultimately we have this equation. This is the canonical form. So if we just make a table of these three forms of hyperbolic, parabolic and elliptic equation, this is the particular table. This is the standard form. If you must remember this form, you must remember all three forms, because you have to ultimately reduce any given equation to this form only, and this form is all considered as the canonical form. And this is the corresponding conditions of hyperbolic, parabolic and elliptic. So I think I will give you some problems to do on your own in the assignment, and you should do that problem for practice, and you should tell me if you could do that problem or not, and if not, I will help you in solving problems. Okay.